Look up at the night sky, and beneath the familiar tapestry of stars lies a hidden universe crackling with invisible energy, a sea of X-rays so vast it bathes the entire cosmos in an eerie glow. This is the cosmic X-ray background, one of space's most profound puzzles. For decades, astronomers have been captivated by this faint, pervasive radiation, a whisper from the depths of the universe that defies easy explanation. Where does it come from? What cosmic engines could produce such a relentless hum of high-energy light? The answers might rewrite our understanding of the universe itself. Imagine standing in a pitch-black room, surrounded by unseen sources of light, each one flickering with secrets. That's the challenge scientists face with the cosmic X-ray background. It's not coming from a single star or galaxy, but from everywhere at once, a diffuse fog of X-rays that fills the spaces between galaxies, between clusters, even between superclusters. Some of it stems from supermassive black holes feasting on matter, some from the remnants of exploded stars, and some from processes so mysterious they've yet to be uncovered. But here's the haunting part. Even when we account for all known sources, a significant portion of this radiation remains unclaimed. Something, or many somethings, are out there hiding in plain sight. Today, we're diving into 25 of the most tantalizing mysteries woven into this cosmic tapestry. From rogue black holes wandering the void to the possibility of entirely new classes of celestial objects, each clue pulls us deeper into the unknown. This isn't just about filling gaps in our knowledge, it's about confronting the edges of our imagination. Because every time we've unraveled one of the universe's secrets, we've found something stranger than we ever dreamed. So let's begin the journey, peeling back the layers of the cosmic X-ray background, one enigma at a time. Who knows what wonders or terrors we might uncover? The first great riddle of the cosmic X-ray background lies in its eerie uniformity, a ghostly veil of high-energy light stretching seamlessly across the heavens. When early X-ray satellites like Uhuru first mapped this diffuse glow in the 1970s, scientists expected jagged variations, bright knots tied to known galaxies or clusters. Instead, they found something far stranger, a near-perfect smoothness, as if the universe had been brushed with an invisible paint of X-rays. This wasn't just unexpected, it was revolutionary. Either countless faint sources, black holes, neutron stars, or distant galaxies were blending together into an indistinguishable haze, or something fundamentally new was at play. The implications shook astronomy to its core. Take a distant highway at night where countless car headlights merge into a single blur of light. That's the conventional explanation. Trillions of individual X-ray sources, each too faint to spot alone, collectively creating the glow. Yet when astronomers tallied up all known objects, active galaxies, quasars, even the hot gas between galaxy clusters, they still couldn't account for the entire signal. A stubborn fraction refused to be explained, whispering of hidden players. Some theories point to primordial black holes, ancient relics from the universe's first moments, evaporating slowly and releasing X-rays as they vanish. Others suggest particles of dark matter, decaying over eons and shedding energy in the process. Both ideas skirt the edge of known physics, hinting at realms beyond our current understanding. What makes this mystery so thrilling is its scale. Unlike a single curious object or event, the diffuse glow is woven into the fabric of the cosmos itself. Every direction we look, the same unanswered questions linger. Modern telescopes like Chandra and XMM Newton have peeled back layers of the mystery, resolving some individual sources, but the deeper truth remains just out of reach. Could the answer rewrite our textbooks on particle physics? Might it reveal entirely new celestial phenomena hiding in plain sight? One thing's certain, until we solve it, the cosmic X-ray background will keep its secrets close, a shimmering enigma written in the language of the universe's oldest light. We know the cosmic X-ray background comes from somewhere, but here's what keeps astronomers up at night. When they tally up all the usual suspects, the math doesn't add up. Active galactic nuclei, those monstrous black holes devouring matter at the centers of galaxies, should be major contributors. So should quasars, blazing with energy as they shine across cosmic distances. Yet, even after accounting for these powerhouses, a staggering chunk of the X-ray glow remains unclaimed. It's like hearing a chorus of voices but realizing half the singers are invisible. This is the resolution problem in action. Think of it like trying to count fireflies in a foggy meadow. Some are bright and obvious, but others flicker so faintly they blend into the haze. Telescopes like Chandra have spotted millions of X-ray sources, but there's a limit to how faint they can see. Below that threshold, entire populations of dim objects could be lurking, black holes too quiet to detect individually, or galaxies shrouded in thick dust, their X-rays muffled like a whisper behind a closed door. Some researchers believe these hidden black holes could be the missing piece, their faint emissions blending into the background like static in a cosmic radio signal. Then there's the wild card, exotic physics. What if some of this glow comes from objects we haven't even imagined yet? Hypothetical entities like quark stars, ultra-dense remnants of dead stars, even stranger than neutron stars, could be leaking X-rays as they slowly decay. Or consider dark matter particles colliding in the voids between galaxies, annihilating in flashes of high-energy light. These ideas hover at the edge of our understanding, tantalizing but unproven. Every time we build a more sensitive telescope, we peel back another layer, only to find new questions waiting. The beauty of this mystery is its humbling scale. We're not just hunting for one missing source, but an entire cosmic demographic entities too faint, too obscured, or too bizarre to spot with current tools. It's a reminder that the universe still holds cards close to its chest. As technology advances, we might finally bring these shadows into the light. Until then, the missing X-ray sources stand as silent witnesses to how much we have yet to discover. The spectrum of the cosmic X-ray background holds a clue so bizarre it scrambles our expectations of how high-energy light should behave. When scientists split this radiation into its component energies, they found something peculiar, an unexpected excess of hard X-rays, the most energetic kind, as if the universe left fingerprints from processes we've never witnessed. Most known sources, like black holes or supernova remnants, produce a predictable mix of energies, but the CXB's spectrum skews strangely toward the high end, like a radio tuned to static between stations, crackling with signals we can't decipher. This anomaly might trace back to the earliest chapters of the cosmos. Picture the universe in its infancy, a seething plasma of particles and energy. Some theories suggest primordial black holes, those hypothetical leftovers from the Big Bang, could be evaporating via Hawking radiation, their final bursts emitting hard X-rays as they wink out of existence. Others propose even wilder ideas. Particles of dark matter drifting through space for billions of years might occasionally decay or collide, releasing energy in the form of these high-energy photons. It's a cosmic detective story where every clue points to physics beyond the standard model. Then there's the curveball, the possibility we're hearing echoes from entirely new celestial objects. Neutron stars, the ultra-dense corpses of dead suns, were once thought to cap at a certain energy output. But what if some extreme variants exist, spinning faster or crushing matter into exotic states we've yet to classify? Magnetars, neutron stars with unimaginably strong magnetic fields, already stretch our understanding. Could there be something even more extreme lurking just beyond detection? The hard X-ray excess might be their calling card. What makes this mystery so electrifying is its refusal to fit neatly into boxes. Every time researchers tweak their models, adjusting the numbers for known sources or factoring in new physics, the spectrum stubbornly resists explanation. It's a reminder that the universe doesn't owe us simplicity. As next-generation telescopes like Athena come online, they'll scan the skies with unprecedented precision, hunting for the origins of these rogue photons. Until then, the CXB's spectrum remains a cosmic cipher, written in light we're still learning to read. Supermassive black holes should be the ultimate cosmic powerhouses, capable of explaining a significant chunk of the cosmic X-ray background. These monsters lurking at the centers of galaxies are anything but quiet. As they devour surrounding gas and dust, matter spirals inward at nearly light speed, forming searing hot accretion disks that glow fiercely in X-rays. Some even launch jets of particles so energetic they can pierce through entire galaxies, lighting up the cosmos like celestial lighthouses. Yet when astronomers add up all this fury, something doesn't align. Their combined output barely scratches the surface of the CXB's total intensity. It's like hearing a symphony where the loudest instruments are barely a whisper in the grand chorus. The disconnect deepens when you consider how these black holes operate. Picture an all-you-can-eat buffet where the hungriest guests somehow leave the table half full. Active galactic nuclei, those supermassive black holes in feeding frenzies, should dominate the X-ray sky. But many are oddly frugal, flickering unpredictably or dimming over cosmic time. Some may be hidden behind thick veils of dust, their X-rays muffled before they reach us. Others might be in a dormant phase, their accretion disks running on fumes. Even when we account for these quirks, the numbers still fall short. There's a glaring deficit, a shadowy gap between what we observe and what the equations demand. Could the answer lie in black holes we're not seeing? Imagine a cosmic census where entire populations are missing from the records. Intermediate mass black holes, those elusive middleweights between stellar corpses and supermassive giants, might be pumping out X-rays undetected. Or perhaps early galaxies hosted hyperactive black holes that have since gone quiet, their radiation only now reaching us as part of the diffuse background. The James Webb Space Telescope has already spotted surprisingly massive black holes in the young universe, suggesting our models of their growth might need revisiting. If these objects were more common or more violent in the past, their faded echoes could still haunt the CXB today. Then there's the wildest possibility: supermassive black holes might not be the only players. Other exotic phenomena, like colliding neutron stars or rogue black holes drifting between galaxies, could be adding their voices to the mix. Some theorists even speculate about cosmic strings' hypothetical defects in spacetime that might emit X-rays when they snap. Until we pinpoint these missing contributors, the true balance sheet of the cosmic X-ray background remains unsettled. What's clear is this: even the universe's most voracious engines can't shoulder the blame alone. The rest of the story is still being written in light we're only beginning to decode. Dwarf galaxies, tiny, faint cousins of grand spirals like the Milky Way, might hold a key piece of the cosmic X-ray background puzzle. These unassuming cosmic neighborhoods, often containing just a fraction of the stars in larger galaxies, were long dismissed as minor players in the high-energy universe. But new research suggests we've underestimated them. Packed with tight-knit stars and turbulent gas, dwarf galaxies could be teeming with X-ray binaries, pairs where a neutron star or black hole strips material from a companion, unleashing intense X-rays. If enough of these binaries ignite across thousands of dwarf galaxies, their combined glow might explain a significant slice of the CXB's lingering haze. The challenge is catching them in the act. Spotting X-ray sources in dwarf galaxies is like trying to pick out a single flashlight in a foggy city viewed from miles away. Their faintness pushes even advanced telescopes to their limits. Worse, many dwarfs are shrouded in dust or hidden behind foreground stars in our own galaxy, masking their high-energy signatures. Recent simulations, however, paint a compelling picture. These diminutive galaxies might host far more X-ray activity than we thought. Some models suggest their low gravity and pristine gas, unchanged by eons of star formation, create perfect conditions for prolific X-ray binaries. Others raise an even bolder idea: intermediate mass black holes, elusive objects hundreds of times heavier than our Sun, could lurk in their cores, quietly radiating X-rays as they consume surrounding matter. Then there's the twist of cosmic evolution. In the early universe, dwarf galaxies were far more numerous, colliding and merging in a chaotic dance. If they harbored even modest numbers of X-ray sources back then, their faded remnants could still contribute to today's background glow. The James Webb Space Telescope has already spotted ancient dwarf galaxies with surprising star formation rates, hinting they might have been X-ray factories in their youth. What makes this mystery so tantalizing is its dual nature. Solving it wouldn't just crack a piece of the CXB enigma, it could rewrite our understanding of how small galaxies shape the cosmos. Are they cosmic dark horses quietly powering the universe's X-ray hum? Or do they hide even stranger phenomena, waiting for sharper telescopes to reveal them? Every flicker of X-rays from these faint realms pulls us closer to an answer. Among the most spine-tingling explanations for the cosmic X-ray background is the idea that we're hearing the dying whispers of primordial black holes, ancient relics born not from collapsing stars, but from the violent turbulence of the Big Bang itself. These hypothetical objects, some as small as an atom yet heavier than a mountain, would have formed in the universe's first chaotic moments when dense pockets of matter collapsed under their own gravity. If they exist, their final moments could solve one of astrophysics' greatest puzzles. Picture a black hole so tiny it fits in your palm, yet radiates energy with ferocious intensity. According to Stephen Hawking's groundbreaking theory, all black holes slowly lose mass through quantum effects near their event horizons, emitting particles until they eventually explode. For primordial black holes nearing the end of their lifespans, this evaporation would unleash a storm of high-energy radiation, including X-rays. Multiply this by trillions of such objects scattered across the cosmos, and you've got a potential explanation for the CXB's pervasive glow. It's like listening to static on a cosmic radio, only to realize it's actually the synchronized last breaths of countless invisible entities. But why hasn't definitive proof emerged? Detecting these elusive objects is like trying to spot fireflies in a hurricane. Primordial black holes could be almost anywhere, floating between stars, lurking in galactic halos, or even hiding within our solar system. Some might pass through Earth undetected, their gravity too feeble to disturb nearby matter. Others could evaporate too quickly, leaving only a fleeting X-ray burst. NASA's Fermi Gamma Ray Space Telescope has hunted for their explosive final moments, but so far, the evidence remains circumstantial at best. The plot thickens when you consider their potential role in dark matter. If primordial black holes make up even a fraction of this invisible cosmic substance, their mergers could produce not just X-rays but gravitational waves, ripples in spacetime detectable by observatories like LIGO. A handful of unexpected LIGO signals have already sparked speculation. Could these be collisions of primordial black holes from the dawn of time? It's a long shot, but if confirmed, it would tie two of the universe's biggest mysteries into one breathtaking solution. Skeptics rightfully point out the gaps. The predicted number of primordial black holes hinges on poorly understood conditions in the early universe, and alternative explanations, like faint galaxies or exotic particles, still hold sway. Yet the theory's elegance is undeniable. It transforms the cosmic X-ray background from a mere afterglow into a cosmic graveyard, humming with the last echoes of entities older than stars themselves. Whether this idea survives future telescopes or fades into obscurity, one thing's certain: the universe loves hiding its greatest secrets in plain sight. Deep in the heart of the cosmic X-ray background, there's a whisper that might trace back to the universe's most elusive substance, dark matter. This invisible cosmic scaffolding, outweighing normal matter 5 to 1, has teased astronomers for decades, revealing itself only through its gravitational pull. But what if its secrets are hiding in plain sight, encoded in the high-energy glow of the CXB? Some theories suggest certain dark matter particles, like sterile neutrinos or WHIM, could decay or annihilate over eons, releasing bursts of X-rays as they vanish. If true, the background radiation isn't just a cosmic fossil, it's a live broadcast from the dark universe itself. Sterile neutrinos, hypothetical cousins to the ghostly particles we already know, are prime suspects. Unlike ordinary neutrinos, which barely interact with matter, sterile neutrinos might occasionally decay, transforming into an X-ray photon and a regular neutrino. The energy signature of this decay would be subtle but distinct, like finding a specific note in a symphony of static. Telescopes like NASA Chandra have scoured the CXB for this telltale signal, focusing on galaxy clusters where dark matter is densely concentrated. A faint emission line around 3.5 kiloelectronvolts, a specific energy level, has popped up in observations, sparking excitement. But the results remain controversial, flickering in and out of detection like a radio station tuning in and out of range. Then there's the case of WHIM, or weakly interacting massive particles. These heavier dark matter candidates might collide in the darkness, annihilating each other in flashes of X-rays. Dwarf galaxies, rich in dark matter but low in competing X-ray sources, are ideal hunting grounds. Experiments like the Hitomi satellite and the upcoming X-RISM mission have trained their sights on these faint systems, searching for excess X-rays that can't be explained by ordinary astrophysics. So far, the data refuses to cooperate, leaving researchers to wrestle with an unsettling possibility. Either dark matter behaves differently than we think, or we're missing a critical piece of the puzzle. The stakes couldn't be higher. Confirming a dark matter connection to the CXB wouldn't just solve one mystery, it would crack open the door to an entirely new branch of physics. Imagine rewriting the rules of the cosmos based on a faint hum of X-rays. Yet the lack of definitive proof has forced scientists to confront alternative explanations. Could the signals be contamination from known sources or artifacts of telescope calibration? Or might dark matter be even stranger, leaving no X-ray trail at all? For now, the hunt continues, a delicate dance between hope and skepticism. Every null result narrows the possibilities, steering us closer to the truth. Whether the answer lies in sterile neutrinos, WHIM, or something beyond our current imagination, one thing's clear: the cosmic X-ray background isn't just light. It's a cryptic message waiting to be decoded, and dark matter might be its most compelling author. The universe isn't just a scatter of galaxies, it's a masterpiece of invisible architecture, a sprawling cosmic web where galaxies cluster along shimmering threads of dark matter and hot gas. These filaments, stretching millions of light years across the void, might hold another clue to the cosmic X-ray background's enigma. Theory suggests the gas trapped in these tendrils should be searingly hot, heated to temperatures so extreme they emit X-rays. If true, the faint glow we see could be the collective breath of the universe's skeletal structure, a whisper of energy from the spaces between everything we know. But why haven't we spotted these X-ray filaments directly? Imagine trying to photograph a spider's web backlit by a floodlight. The threads are there, but their delicate glow drowns in the glare. That's the challenge astronomers face. The cosmic web's gas is so diffuse, its X-ray signal drowns beneath brighter sources, active galaxies, exploding stars, even our own Milky Way's high-energy haze. Current telescopes like Chandra and XMM Newton can only catch hints of this emission when peering at massive galaxy clusters, where filaments converge and thicken enough to stand out. The rest remains a ghostly backdrop just beyond the edge of detection. The stakes are enormous. Confirming this component of the CXB wouldn't just fill a gap in the budget of cosmic light, it would validate our entire picture of how the universe organizes itself. Simulations show the Webb's filaments should contain nearly half the universe's normal matter, a staggering amount currently missing from our inventories. If future telescopes could map this faint X-ray glow, it would be like turning on a black light in a dark room, revealing the hidden veins of the cosmos for the first time. Enter missions like Athena, slated to launch in the 2030s. With sensitivity 100 times greater than current observatories, it could finally tease out the Webb's X-ray signature from the noise. Another contender, Lynx, would combine razor-sharp resolution with deep field surveys, potentially spotting individual filaments as they thread between galaxies. The payoff, a revolutionary census of the universe's baryonic matter. The ordinary atoms were made of currently lost in the voids, yet even if these missions succeed, mysteries will linger. Some models suggest the Webb's gas might be turbulent, stirred by collisions or energy injections from ancient quasars, altering its X-ray fingerprint. Others propose magnetic fields threading the filaments could skew their emissions in unexpected ways. Every answer births new questions, but that's the thrill of the hunt. The cosmic web isn't just structure, it's a living record of the universe's growth, written in X-rays we're only now learning to read. What if we're on the verge of a paradigm shift? Mapping these filaments wouldn't just solve a piece of the CXP puzzle, it could redefine our place in the cosmos. We'd no longer be island hopping between galaxies, but navigating a luminous highway system, its roads paved with light we've only just begun to see. The universe has always been more connected than it appears. Soon, we might finally grasp the threads that bind it all together. Sandwiched between galaxies, in the void most would call empty, lurks a phantom, a sea of ionized gas so hot it glows in X-rays, yet so sparse it's nearly invisible. This is the warm, hot intergalactic medium, or WHIM, a theorized cosmic reservoir that could hold up to half the universe's normal matter. For decades, astronomers have chased this elusive substance, knowing it must exist but struggling to catch even a glimpse. If found, it could solve two puzzles at once, the missing matter problem and a chunk of the cosmic X-ray background's origin. Yet hunting the WHIM is like trying to photograph steam rising from a glacier. Its signals are faint, diffuse, and maddeningly easy to overlook. Why is it so hard to spot? Picture a cloud so wispy that light passes through it almost uninterrupted. The WHIM gas is 1,000,000 times less dense than the air you breathe, heated to millions of degrees by shocks from galaxy collisions and cosmic web formation. At these temperatures, it should emit soft X-rays blending into the CXP's haze, but its emission is drowned out by brighter sources, like trying to hear a whisper in a roaring stadium. Instead, astronomers turn to a clever workaround, absorption lines. When light from distant quasars passes through the WHIM, specific wavelengths get absorbed, leaving fingerprints in the quasar's spectrum. It's like shining a flashlight through fog. The dimmer the beam gets, the more you know about what's in the way. The challenge, these absorption lines are vanishingly subtle. Oxygen ions, stripped of most of their electrons by the WHIM heat, absorb X-rays at precise energies. Spotting these dips requires instruments with exquisite sensitivity, like the Chandra X-ray Observatory or Japan's Hitomi satellite. Even then, success is rare. In 2016, Hitomi detected a tantalizing absorption line in the Perseus cluster, hinting at warm gas along the line of sight, but the satellite's tragic failure cut the investigation short. Later attempts with other telescopes have yielded conflicting results, leaving the WHIM existence just beyond confirmation. The stakes couldn't be higher. If the WHIM is real, it's the hidden backbone of the cosmic web, tracing the filaments where galaxies form and collide. Its discovery would rewrite the inventory of the universe, accounting for the missing baryonic matter that simulations insist must exist. Some theories even suggest the WHIM could be tangled with dark matter, its distribution revealing clues about the invisible scaffolding shaping the cosmos. Yet skeptics caution against premature celebration. alternative explanations like turbulent gas within galaxy clusters could mimic the WHIM signatures. Others argue the absorption lines might come from unrelated clouds of cooler gas, adding noise to an already murky signal. The answer likely lies with next-generation tools like ESA's Athena mission, whose unprecedented spectral resolution could finally isolate the WHIM whisper from the cosmic static. What makes this hunt so compelling is its double-or-nothing gamble. Succeed, and you've mapped the universe's hidden plumbing. Fail, and you're forced to confront an unsettling truth. Half the ordinary matter in existence has vanished without a trace. Either outcome forces us to rethink our place in the cosmos. The WHIM isn't just missing matter, it's a test of whether we truly understand the universe's grand design. Until we find it, the question lingers: is the cosmos playing hide and seek, or are we just not seeing the board? Some of the brightest X-ray beacons in the universe defy every expectation, objects so luminous they shouldn't exist, yet there they glow, scattered across galaxies like cosmic lighthouses. These are ultra-luminous X-ray sources, or ULCs, and they're pumping out X-rays at rates that shatter theoretical limits. A typical stellar mass black hole, born from a collapsed star, can only emit so much energy before physics says it should tear itself apart. Yet ULXs outshine this limit by hundreds or even thousands of times, leaving astronomers scratching their heads. Are these rogue black holes breaking the rules, or could they be something far stranger, missing links in the black hole family tree? The leading theory points to gluttonous stellar mass black holes, gorging on gas at rates so extreme they briefly defy the Eddington limit, the point where radiation pressure should blow away their food supply. Picture a candle flame suddenly flaring like a bonfire, its glow overwhelming the wick's ability to sustain it. Some ULXs might achieve this by feeding in messy, chaotic bursts, swallowing gas faster than it can radiate energy away. Others could be funneling matter along tightly wound magnetic fields, focusing their emissions into narrow beams that appear brighter when pointed at us. It's a cosmic sleight of hand, turning modest black holes into apparent monsters through sheer feeding frenzy. But here's where the plot twists: not all ULXs play by these rules. A handful, like the famous ESO 243-15, exhibit behaviors that hint at something heavier. These outliers might be intermediate mass black holes, the long-sought middleweights between stellar corpses and supermassive giants. Weighing in at thousands of solar masses, they'd naturally emit more X-rays without breaking physics, yet confirming their existence has been like chasing shadows. Their light blends with crowded star fields, and their telltale gravitational tugs are drowned out by galactic noise. If they're real, they could be the dark horses of the cosmic X-ray background, contributing a steady hum of high-energy light from countless galaxies. Even if ULXs are everywhere, though, they can't shoulder the CXB's full burden. For one, their numbers don't add up. There simply aren't enough to explain the background's pervasive glow. They're also unevenly distributed, clustered in star-forming regions rather than spread evenly across the cosmos. Some might be transient, flaring up and fading before telescopes can catalog them, while others could be hidden behind veils of dust, their X-rays muffled. It's as if we've found a few blazing campfires in a dark forest, only to realize they can't account for the distant glow on the horizon. The deeper mystery is what ULXs reveal about black hole diversity. Could they represent a spectrum of feeding styles, magnetic geometries, or even exotic states of matter? Some models suggest super Eddington black holes might wrap themselves in thick disks of gas, acting like cosmic pressure cookers that redirect energy vertically. Others speculate about Thorne-Zitkow objects, hypothetical hybrid stars with black holes at their cores, blurring the line between star and monster. Every ULX we study chips away at the boundaries of known physics, hinting that the universe has more ways to make light than we've dreamed. What makes ULXs so tantalizing isn't just their glow. It's their refusal to fit neatly into categories. They might be stellar imposters, cosmic middleweights, or something entirely new. Until we solve their riddle, they'll keep challenging our assumptions, one X-ray photon at a time. And while they might not close the book on the cosmic X-ray background, they're proof that the universe still holds surprises in its brightest corners, outshining our expectations and sometimes our understanding. X-ray binaries are the universe's most dramatic duos, pairs where a black hole or neutron star locks in a lethal dance with a companion star, slowly siphoning off its gas. As this stolen matter spirals inward, it heats to millions of degrees, erupting in X-rays so intense they can outshine entire galaxies. These systems should be major contributors to the cosmic X-ray background, but here's the catch: their light isn't steady. Some flare violently before fading to near darkness, while others flicker unpredictably like a candle in the wind. This variability makes them cosmic wildcards, blending into the background's haze in ways that might have fooled our telescopes. Take the famous Cygnus X1, a black hole slurping gas from a supergiant star. From Earth, it's a brilliant beacon, but zoom out to a distant galaxy, and its flickering could make it vanish into the noise. That's the core problem. Current models often treat X-ray binaries as if they emit at constant rates, like light bulbs left on. In reality, their output spikes and dips based on the whims of their feeding cycles. When surveys tally up their contributions, the dim phases might get overlooked entirely, as if the universe's ledger only counted the loudest voices. The result, a glaring underestimate of how much these binaries truly add to the CXP's glow. Distance adds another layer of confusion. In far-off galaxies, even the brightest X-ray binaries blur together, their individual pulses smearing into a collective hum. It's like standing outside a stadium. Up close, you hear every cheer and chant, but from miles away, it merges into a dull roar. Telescopes struggle to resolve these faint, distant sources, especially when they're nestled in star-forming regions shrouded by dust. Some studies suggest we might be missing up to half the X-ray binaries in early galaxy systems, whose accumulated light could tip the scales on the background's origin. Then there's the question of demographics. Not all X-ray binaries are created equal. Low-mass systems where a black hole orbits a sun-like star tend to be quieter and more stable. High-mass binaries paired with massive stars are volatile beasts, prone to outbursts that can briefly outshine their host galaxies. If the early universe favored one type over the other, their footprint on the CXP would shift dramatically. Recent simulations hint that young galaxies, rich in short-lived massive stars, might have hosted swarms of these high-mass binaries, their combined emissions echoing across time to reach us now. The implications are profound. If even a fraction of these variables have been undercounted, the cosmic X-ray background's ledger needs revision. Future missions like Lynx, with its keen eye for faint sources, could finally unmask these hidden contributors, peeling back the layers of cosmic noise to reveal the binaries beneath. Until then, they remain elusive players in the high-energy universe, sometimes whispering, sometimes shouting, but always shaping the light we're straining to understand. Some galaxies refuse to play by the rules, massive structures brimming with dark matter and gas, yet almost completely devoid of stars. These cosmic ghosts, known as dark galaxies, lurk invisibly across the universe, their presence betrayed only by subtle gravitational tugs or faint wisps of glowing gas. If they exist in significant numbers, they could be stealth contributors to the cosmic X-ray background, their hidden black holes or superheated gas adding to the pervasive high-energy hum we've yet to fully explain. Picture a galaxy like our Milky Way, but with a cruel twist, nearly all its stars snuffed out before they could ignite. Perhaps early turbulence or a lack of dense gas pockets prevented stellar birth, leaving behind a shadowy realm of swirling hydrogen and dark matter. Within these star-starved realms, supermassive black holes could still lurk in the darkness, feeding on sparse gas and radiating X-rays without the usual stellar fanfare. Alternatively, collisions between gas clouds in these systems might heat material to extreme temperatures, producing faint but widespread X-ray emissions that blend into the CXB's fog. The challenge is proving they're out there. Without stars, dark galaxies don't shine in optical light, slipping past traditional surveys. Astronomers rely on tricks like gravitational lensing, where the galaxy's mass bends light from objects behind it to spot their subtle fingerprints. A handful of candidates have emerged, like Dragonfly 44, a dim galaxy with the mass of the Milky Way but only 1% of its stars. Others reveal themselves through radio waves, their cold hydrogen gas betraying colossal structures hiding in plain sight. Yet the most tantalizing clues come from mismatches in the cosmic ledger. When researchers tally up the gravity needed to explain how galaxies move in clusters, there's often more mass than visible stars and gas can account for. Dark galaxies could be part of that missing mass, their sheer abundance filling the gaps. Some simulations suggest there might be hundreds of these phantoms for every bright galaxy we see, a hidden population quietly shaping the universe's structure. The hunt now turns to X-ray signatures. If dark galaxies host even modest black holes or turbulent gas, their collective emissions could nudge the CXB's numbers. Upcoming telescopes like the European Space Agency's Athena might catch these whispers, especially if they're clustered near brighter galaxies where gas interactions could spark X-ray flares. Another hope lies in synchrotron radiation, high-energy light produced when particles spiral around magnetic fields in these gas-rich systems. What makes dark galaxies so compelling isn't just their potential role in the CXB puzzle, it's what they say about galaxy evolution's dark side. They could be cosmic dead ends, failed experiments where star formation fizzled, or they might be primordial relics frozen in an early state before stars arose. Either way, their existence would force us to rethink how galaxies are born, live, and sometimes fade into the darkness. For now, they remain phantoms, ghosts in the cosmic machine, whispering through gravity and the faintest light. But if even a fraction of them are real, they could be the universe's quietest revolutionaries, reshaping our understanding of what a galaxy can be. The question isn't just whether they're adding to the X-ray background, but how many more secrets they're keeping in the shadows. The cosmic X-ray background appears steady, a constant hum across the sky, but what if that's an illusion? Beneath its seemingly uniform glow, subtle flickers might betray hidden dramas playing out over cosmic time. Unlike visible starlight, which can take millions of years to reach us, X-rays often signal violent, transient events. Stars shredded by black holes, galaxies colliding, or the afterglows of gamma-ray bursts. If even a fraction of these cataclysms leave traces in the CXB, their combined fingerprints could create faint ripples in the background's intensity, shifting slightly as the universe evolves. Tidal disruption events offer a prime example. Imagine a star wandering too close to a supermassive black hole, its gas stretched into a luminous stream as it's devoured. For months, this feast emits a flare of X-rays bright enough to outshine entire galaxies. While individual events are rare, the universe is vast. Countless such disruptions could be happening at any moment, their light blending into the CXB. Studies using NASA's Swift satellite have spotted these flares in nearby galaxies, but the real question is whether their echoes persist across deep space, contributing to the background's faint variability. Some models suggest they might account for up to 10% of the CXB's unresolved flux, flickering like fireflies in a fog. Gamma-ray bursts add another layer of intrigue. These titanic explosions, thought to accompany the births of black holes, unleash jets of energy so powerful they're visible across the observable universe. While their initial blast lasts mere seconds, their X-ray afterglows can linger for weeks. If enough of these afterglows overlap in time, their combined light might imprint a barely detectable pulse onto the CXB. The challenge is isolating these signals from the noise, like trying to hear individual raindrops in a thunderstorm. Then there's the slow dance of cosmic evolution. Billions of years ago, galaxies were smaller, denser, and more prone to collisions, hosting far more active black holes per capita than today. As these black holes flared and faded, their collective X-rays would have built up over eons, meaning the CXB we see now is actually a layered snapshot, a mix of ancient emissions and newer, fainter additions. Telescopes like Chandra have glimpsed this time dependence by studying distant galaxy clusters, where the X-ray glow subtly shifts with redshift, a telltale sign of changing conditions over cosmic history. The wild card, unknown transients. For every tidal disruption or gamma-ray burst we catch, there could be dozens of exotic events we've yet to classify. Black hole mergers, quark nova eruptions, or collapses of strange matter. These might leave fleeting X-ray signatures too rare or faint to spot individually, yet numerous enough to tint the CXB when summed together. Projects like the Vera Rubin Observatory, while optical, could revolutionize this hunt by flagging strange behaviors that X-ray telescopes then investigate. What makes this mystery so tantalizing is its paradox. The CXB's apparent stability might be masking a universe of chaos. If we could speed up time, watching eons pass in seconds, would the background shimmer like heat haze on a desert horizon, or does it pulse to rhythms we've yet to decode? Every flicker, no matter how slight, is a clue, a whisper from events too vast or too distant to see clearly. The answer won't just illuminate the CXB's origins, it'll reveal how alive the high-energy universe truly is, even in its quietest moments. One of the most humbling realizations in modern cosmology is this: we can account for barely half the normal matter that should exist in the universe. Not dark matter, plain old atoms, the stuff stars and planets are made of. Where did these missing baryons go? The cosmic X-ray background might hold the answer, pointing to vast reservoirs of superheated gas hiding between galaxies. If we follow the X-ray glow, it could lead us straight to the universe's greatest game of hide and seek. Start with what we know. The Big Bang's afterglow, the cosmic microwave background, gives us a precise recipe for how much ordinary matter, protons, neutrons, and electrons, the universe began with. Yet when astronomers tally up all the visible stars, galaxies, and cold gas clouds, they come up shockingly short. Over half the baryons are unaccounted for, a discrepancy so glaring it's called the missing baryon problem. For decades, this cosmic accounting error nagged at scientists until they turned their gaze to X-rays. The leading suspect, a diffuse ocean of ionized gas, scorched to temperatures between 100,000 and 10 million degrees, drifting through intergalactic space. At these extremes, hydrogen and helium lose their electrons and emit soft X-rays, subtly boosting the cosmic X-ray background's haze. But spotting this gas is like trying to see steam rising from a highway on a summer day. It's there, but nearly transparent. Telescopes can't image it directly, so astronomers use clever workarounds, like hunting for its fingerprints in the light of distant quasars. As that light passes through the hot gas, specific X-ray wavelengths get absorbed, leaving minuscule dips in the quasar spectrum. It's the universe's version of a forensic trace. The challenge is these signals are vanishingly faint. Early hints emerged from the Chandra X-ray Observatory, which detected absorption lines matching highly ionized oxygen in the intergalactic medium. Later, Europe's XMM Newton spotted similar signatures, suggesting the gas might be arranged in tangled filaments along the cosmic web, the sprawling scaffold of dark matter that shapes the universe's large-scale structure. If confirmed, these filaments wouldn't just solve the missing baryon problem, they'd reveal the hidden plumbing of the cosmos, channels where matter flows between galaxies like water through a sponge. Yet skepticism lingers. Some argue the absorption lines could come from gas within galaxy clusters, not the true intergalactic medium. Others note the signals are so weak they flirt with the noise threshold of current instruments. The breakthrough may require next-generation observatories like Athena, whose advanced spectrometers could finally map this elusive gas in 3D, revealing whether it spread uniformly or clumped in predictable ways. The stakes go beyond bookkeeping. If these baryons are indeed hiding in intergalactic gas, their distribution could unlock secrets about how galaxies form and evolve. Simulations suggest this hot plasma might act as a cosmic pressure valve, regulating the inflow of fresh matter into galaxies and even quenching star formation in some cases. It's a dynamic, ever-shifting component of the universe's ecosystem, one we've barely begun to understand. What makes this mystery so captivating is its scale. We're not searching for a few stray atoms, but for an entire phase of matter, woven into the voids between every galaxy. The cosmic X-ray background could be our roadmap to finding it, a faint trail of high-energy light left by the universe's most overlooked inhabitants. Solve this, and we don't just balance the cosmic ledger, we rewrite our understanding of where and how the ordinary stuff of existence chooses to hide. Hidden within the cosmic X-ray background might be echoes of the universe's most chaotic era, the first billion years, when galaxies were just assembling and supermassive black holes burst into existence faster than physics should allow. This epoch, known as cosmic dawn, was a firestorm of creation, gas collapsing into stars, stars colliding into black holes, and those black holes ballooning to sizes that still baffle astronomers. If traces of that violence linger in the CXB, decoding them could rewrite the story of how everything began. The James Webb Space Telescope has already peeled back the curtain on this era, spotting galaxies so early and bright they defy expectations. But while Webb captures their starlight, X-ray telescopes hunt something darker. The black holes at their cores voraciously devouring matter and spewing X-rays. Some of those emissions, after traveling for over 13 billion years, could still be trickling into the CXB like whispers from a distant past. The challenge: disentangling these ancient photons from the cacophony of newer sources. It's like trying to pick out a single note from a symphony played at half speed across cosmic time. One clue lies in the energy signature of these early X-rays. The young universe was denser, hotter, and brimming with pristine gas, which might have altered how black holes emitted radiation. Simulations suggest the first supermassive black holes grew in fits and starts, their accretion disks flickering like campfires in a hurricane. Unlike today's steady giants, these primordial monsters could have flared violently, their X-rays carrying a distinct spectral fingerprint, one that might still faintly tinge the CXB's glow. Then there's the puzzle of how these black holes grew so big so fast. Webb's discovery of fully formed galaxies in the universe's infancy only deepens the mystery. Did they start as seeds from collapsed supermassive stars, or did they balloon by swallowing gas at impossible rates? The CXB could hold answers. If telescopes like Athena or the proposed Lynx mission detect an excess of hard X-rays, the kind produced by rapid, chaotic feeding, it would support the idea of an early universe teeming with ravenous black holes on a growth spree. What makes this hunt so electrifying is the potential for serendipity. The first billion years were a laboratory of extremes where conditions existed that we'll never see again. If the CXB preserves even a fraction of that chaos, it could reveal phenomena we've never imagined: black holes born from direct gas collapse, or dark matter interactions sparking unexpected X-rays. Every photon from that era is a time capsule, carrying secrets from a time when the rules themselves might have been different. The ultimate prize, a fossilized snapshot of cosmic dawn, not in starlight but in X-rays. By cross-referencing Webb's deep field images with X-ray surveys, astronomers could one day map how the first black holes lit up the darkness, their radiation slowly blending into the background we see today. It wouldn't just solve a mystery, it would give us front-row seats to the universe's most explosive opening act. If the cosmic X-ray background were a perfect symphony, each note would ring out at identical volume across the heavens, but nature loves imperfections. Zoom in close enough and faint variations emerge across the X-ray sky, patches where the globe brightens or dims by fractions of a percent. These anisotropies, tiny deviations from perfect smoothness, are cosmic breadcrumbs, hinting at structures so vast they could redefine our place in the universe. Picture the night sky as a tapestry woven with threads of dark matter and hot gas. On the largest scales, galaxies cluster along invisible filaments, forming a cosmic web that stretches across billions of light years. When X-rays pass through these dense knots, their light subtly intensifies like headlights brightening through fog. Similarly, voids, the empty deserts between galactic threads, leave dimmer patches where fewer X-ray photons reach us. These fluctuations are whispers of the universe's skeleton, imprinted on the CXB's glow. Yet mapping them is like trying to trace shadows in a candlelit room. The signals are buried under noise from foreground sources and instrumental limits. The real intrigue lies in the outliers regions where the anisotropies defy expectations. Some patches glow brighter than any known cluster should allow, as if hidden superstructures lurk just beyond our vision. Others show eerie voids too large to fit standard models of cosmic evolution. One particularly baffling cold spot, detected by the ROSAT satellite in the 1990s, spans over 30 degrees of sky with no obvious explanation. Could these anomalies trace back to primordial density fluctuations from the Big Bang itself? Or might they signal something more exotic, like bubble-like domains where dark matter behaves differently? Complicating matters is the dance of overlapping signals. The CXB's anisotropies don't just reflect today's universe, they're a palimpsest of every emission across cosmic time. Nearby galaxy clusters imprint sharp, bright knots, while distant quasars from the universe's youth contribute a fainter, more diffuse pattern. Disentangling these layers requires next-level statistical analysis, akin to identifying individual instruments in an orchestra by their reverberations alone. Projects like the eROSAT All-Sky Survey have made strides, revealing a web-like correlation between X-ray clumps and known superclusters, but the matches aren't perfect. Some structures in the CXB have no optical counterparts, suggesting we're missing entire chapters in the universe's architectural blueprint. Theoretical models struggle to keep up. Simulations that beautifully replicate the cosmic web's visible structure often underestimate the CXB's patchiness, hinting that our understanding of gas physics or black hole fueling might be incomplete. Some astrophysicists propose that undiscovered populations of wandering supermassive black holes ejected from galaxies during collisions could be seeding these anomalous hotspots. Others point to the warm-hot intergalactic medium, theorizing its distribution might be lumpier than predicted, with dense pockets acting like cosmic lenses to amplify X-rays from behind them. What makes these anisotropies so transformative is their potential to reveal the invisible. Dark matter's gravitational pull sculpts the cosmic web, but it's the ordinary matter, the gas and black holes, that lights up in X-rays. By comparing the CXB's fluctuations with gravitational lensing maps, astronomers could finally trace how dark and visible matter intertwine across the largest scales. It's a new frontier in cosmic cartography, where every irregularity holds clues to forces we've yet to name. The next leap will come from missions like Athena and the proposed X-ray surveyor, whose razor-sharp resolution could isolate individual contributions to the CXB's patchwork. Imagine peeling back layers of cosmic history with each observation, decoding how clusters grew, black holes flickered, and gas cooled over billions of years, all from faint variations in an all-sky glow. The anisotropies aren't just noise, they're the universe's way of keeping its deepest structures just out of focus, daring us to look closer. At the far edge of the cosmic X-ray background spectrum lies a stubborn anomaly, a high-energy tail of X-rays so powerful they defy conventional astrophysics. These aren't your everyday photons emitted by black holes or hot gas. They're the cosmic equivalent of a scream in the dark, packing energies that challenge our understanding of how the universe operates. Where do these extreme X-rays come from? The answer might rewrite the rules of particle physics or reveal celestial monstrosities we've yet to imagine. Picture a cosmic particle accelerator, far larger and more violent than anything we could build on Earth. Some theories point to blazars, supermassive black holes at the cores of galaxies, whose jets of plasma happen to point directly at us. These jets can accelerate particles to near light speeds, producing X-rays of staggering energy. Yet when astronomers tally up known blazars, their combined output doesn't fully account for the CXB's high energy excess. There's a gap, and it's widening with every observation. Then there's the wild card, action-like particles, hypothetical entities born from string theory. These ghostly particles could convert into X-rays when they encounter magnetic fields, like cosmic chameleons shifting form. If real, they'd leave a telltale signature in the CXB's highest energies, a subtle bump in the spectrum that current telescopes strain to detect. Experiments like the CERN Action Solar Telescope hunt for similar conversions in controlled settings, but the universe might already be flaunting evidence in the X-ray background. But let's not overlook the carnage of the cosmos. Supernova on steroids could unleash gravitational shockwaves capable of accelerating particles to extreme energies, their afterglows lingering as faint X-ray echoes. Even rarer black hole mergers might produce transient bursts of high-energy radiation as their event horizons twist spacetime into knots, the challenge. These events are fleeting, and catching them in the act is like trying to photograph lightning with a slow shutter speed. The implications stretch beyond astrophysics. If the high-energy tale stems from new physics, it could hint at dimensions beyond our own or forces outside the standard model. Some theorists even speculate about decaying dark matter, with particles massive enough to release X-rays as they fracture. Each possibility teeters on the edge of science fiction until a telescope like the proposed Athena mission trains its gaze on the sky, separating signal from noise with unprecedented precision. For now, the CXB's high-energy tail remains a cosmic Rorschach test. To some, it's a signpost to undiscovered particles. To others, evidence of celestial violence we've barely begun to catalogue. One thing's certain, whatever's producing these photons operates at the limits of known physics, in realms where the universe stops playing by the rules we've written. Until we solve it, this mystery stands as a reminder the cosmos still holds its most extreme secrets close, written in light too powerful to ignore. Stars don't just burn out quietly. Some meet far more violent ends, torn apart by the gravitational fury of black holes in events so bright they briefly outshine entire galaxies. These tidal disruption events, or TD, unleash torrents of X-rays as stellar debris spirals into oblivion, creating flares visible across the cosmos. What makes them fascinating is not just their drama, but their potential role in the cosmic X-ray background. Could these cataclysms, fleeting as they are, leave a lasting mark on the universe's high-energy hum? The mechanics are as brutal as they are mesmerizing. When a star wanders too close to a supermassive black hole, tidal forces stretch it like taffy, shredding it into a stream of gas. Half the material gets ejected into space, while the rest forms a searing accretion disk around the black hole, glowing fiercely in X-rays. For months, this feast lights up the cosmos, often peaking at luminosities 1,000 times brighter than our sun's total output over its entire lifetime. The catch: these flares fade fast, leaving behind only echoes in the data archives of telescopes. If enough of them flicker across the universe at any given moment, their combined afterglow might blend into the CXB's unresolved haze like fireworks flashing in a foggy sky. The math hints at their hidden influence. Current estimates suggest a typical galaxy hosts a TD roughly once every 10,000 years, but with billions of galaxies in the observable universe, that translates to hundreds of these events lighting up every day. While individually rare, their collective output could be substantial. Some models propose TDs might account for up to 10% of the CXB's unresolved flux, especially at higher energies where their X-ray signatures peak. The challenge is proving it. Most TDs detected so far live in relatively nearby galaxies, where telescopes like Swift and Chandra can spot their rise and fall. Fainter, more distant events likely slip past unnoticed, their light diluted into the background's noise. Then there's the wild variability in how TDs behave. Not all tidal disruptions are created equal. In galaxies with dormant black holes, the sudden influx of fresh gas can trigger a dramatic X-ray outburst. But in active galaxies where black holes already have steady diets, the signal might be muffled by pre-existing accretion disks. Even stranger, some TDs produce more ultraviolet or optical light than X-rays, depending on the star's composition and the black hole's spin. This diversity makes them cosmic chameleons, some bright in the CXB's energy range, others nearly invisible. The key to solving this puzzle lies in next-generation surveys. Projects like the Vera Rubin Observatory, set to scan the entire southern sky every few nights, could spot thousands of TDs in optical light, flagging them for X-ray follow-up. Meanwhile, missions like ESA's Athena will hunt for their high-energy counterparts with unprecedented sensitivity. If a significant fraction of these events pump X-rays into the cosmos, their cumulative glow might finally be unmasked in the CXB's finer details. What makes TDs so tantalizing isn't just their potential contribution to the background, it's what they reveal about black holes themselves. Every disruption is a natural experiment probing how matter behaves under extreme gravity. Some flares flicker unpredictably, hinting at chaotic accretion flows. Others show bizarre delays between the star's destruction and the X-ray flare's peak, suggesting debris might orbit for years before finally plunging in. These quirks could reshape our understanding of how black holes grow and how often when two neutron stars collide, the universe holds nothing back, a cataclysm so intense it ripples spacetime itself and forges elements heavier than iron in its fury. These mergers, detected through gravitational waves by observatories like LIGO, are already cosmic landmarks, but could their aftermath, a lingering glow of X-rays, be quietly feeding the cosmic X-ray background? The answer might rewrite our understanding of how the heaviest elements spread through the cosmos and what happens when dead stars dance too close. Take GW170817, the first neutron star merger caught by LIGO in 2017. Alongside gravitational waves, telescopes witnessed a kilonova, an explosion 1,000 times brighter than a typical nova, painting the sky with freshly minted gold, platinum, and uranium. But what followed was even stranger. Months later, Chandra detected an unexpected X-ray afterglow, far brighter and longer lasting than models predicted. Instead of fading quickly, the emission plateaued as if something, perhaps a newly formed black hole or a magnetized debris cloud, was still churning out high-energy light. If even a fraction of neutron star mergers leave such persistent echoes, they could collectively tint the CXB's haze like embers smoldering long after a wildfire. The physics behind this is fiendishly complex. During a merger, neutron stars don't just vanish. They collapse, spin wildly, or explode, leaving behind either a heavier neutron star or a black hole. If a neutron star survives, its unimaginably strong magnetic field could power X-rays for years, like a cosmic dynamo. If a black hole forms instead, falling debris might swirl in a temporary disk, glowing in X-rays until the last scraps vanish beyond the event horizon. Some simulations even suggest mergers could launch jets of particles at near light speed. If those jets slam into surrounding gas, they'd produce shockwaves bright in X-rays. The problem, we've only observed a handful of these events and no two behave exactly alike. This is where LIGO and Chandra make a perfect team. Gravitational wave detectors pinpoint mergers while X-ray telescopes hunt for their aftermath. Future upgrades to LIGO, like the planned Cosmic Explorer, will detect mergers across billions of light years, vastly expanding the sample size. Meanwhile, Chandra's keen eye could track how often these events leave X-ray ghosts and for how long. Already, tentative correlations hint at a pattern. Some patches of the CXB appear slightly brighter along lines of sight where gravitational wave events cluster, as if the universe is keeping a receipt of past collisions. But skeptics raise valid counterpoints. Not all neutron star mergers may produce long-lived X-rays. Some could fizzle out quickly if their debris disperses too thinly or falls into a black hole too fast. Others might be obscured by dust, their light absorbed before reaching us. Worse, the CXB's smoothness suggests any merger contribution must be finely balanced. Too many X-ray afterglows would create noticeable clumps, while too few would leave the signal drowned out by other sources. The implications stretch far beyond the CXB. If mergers pump significant X-rays into the cosmos, they could also be spreading heavy elements like cosmic gardeners, seeding galaxies with the raw materials for planets and life. Every flicker of afterglow might trace the dispersal of gold forged in a stellar apocalypse. Future missions like ESA's Athena could finally settle the debate, mapping X-ray echoes across deep time. Until then, neutron star mergers remain both creators and riddles, their full impact still written in light we're learning to decode. Deep within galaxies across the cosmos, monsters lurk behind thick curtains of dust, supermassive black holes furiously devouring matter, their brilliance muffled like a flashlight wrapped in blankets. These are obscured active galactic nuclei, or AN, and they might hold the key to balancing the cosmic X-ray background's ledger. While their unobscured cousins shine brightly in X-rays, these hidden beasts absorb much of their own high-energy light, re-emitting it as infrared radiation or scattering it in unpredictable directions. The result, a cosmic game of hide and seek where some of the universe's most energetic objects remain nearly invisible to our telescopes. Think of an AGN as a lighthouse shrouded in fog. From certain angles, you might catch glimpses of its beam piercing through, while from others, only a dull glow hints at its presence. That's precisely the challenge with obscured AGN, their orientation matters. When a supermassive black hole's accretion disk is viewed edge-on, the surrounding torus of gas and dust acts like a blindfold, absorbing X-rays before they escape. Some radiation gets rerouted, heating the dust until it glows in infrared. Other photons make it out only after ricocheting through space like a pinball, arriving at Earth with their origins scrambled. This cosmic trickery means traditional X-ray surveys miss entire populations of AGN, skewing our census of high-energy sources. The numbers are staggering. Studies suggest obscured AGN could outnumber their unobscured counterparts by 3 to 1, forming the silent majority of cosmic black hole activity. If true, their combined X-ray output, though dimmed, might resolve a significant chunk of the CXB's unexplained flux. The problem is proving it. For decades, telescopes like Chandra and XMM Newton struggled to peer through the dust, catching only the brightest leaks. The breakthrough came from pairing X-ray data with infrared observations, where the dust's thermal glow betrays these hidden monsters. NASA's A WISE mission scanning the sky in infrared revealed thousands of galaxies that looked ordinary in visible light but blazed like beacons at longer wavelengths. Follow-up X-ray studies confirmed many hosted AGN buried under layers of cosmic soot. But the plot thickens with Compton-thick AGN, the most heavily obscured black holes, where the gas is so dense even X-rays get absorbed almost completely. These require indirect detection methods like spotting the faint fluorescence of iron atoms in their vicinity, excited by the trapped radiation. Surveys now suggest Compton-thick AGN could contribute up to 20% of the CXB's unresolved emission, their light so filtered it blends seamlessly into the background. Imagine trying to count invisible campfires by the heat they leave in the air. That's the precision needed to unmask these phantoms. The implications ripple across cosmology. If obscured AGN dominate the CXB, they'd rewrite our understanding of black hole growth and galaxy evolution. Their obscuration might not be permanent. Outbursts of energy could blow away their dusty shrouds, transitioning them into visible AGN over millions of years. This means the CXB we observe today might be a snapshot of black holes caught mid-transformation, a dynamic mix of hidden and revealed monsters. Future missions like NASA's Spherex and ESA's Ariel will map infrared skies with unprecedented detail, potentially exposing millions more of these hidden giants. What makes this mystery so thrilling is its defiance of simplicity. The obscured AGN paradox isn't just about missing light, it's about how the universe hides its most violent engines in plain sight, forcing us to rethink how we observe the cosmos. Every new detection peels back another layer of dust, revealing just how much we've underestimated the darkness. Starburst galaxies are the universe's fireworks factories, cosmic cauldrons where stars form at breakneck speeds, sometimes hundreds per year compared to our Milky Way's sedate 1 or 2. These frenzied nurseries don't just make stars, they destroy them in spectacular supernova, filling space with shock waves and searing plasma that glow fiercely in X-rays. This stellar pandemonium creates a high-energy fog that might permeate the cosmic X-ray background, especially if similar chaos dominated the early universe when galaxies were younger and wilder. Picture the Tarantula Nebula in the Large Magellanic Cloud, scaled up 1,000-fold. Massive stars live fast and die young here, their powerful winds colliding to heat gas to millions of degrees. Each supernova explosion pumps more energy into the mix, creating bubble-like cavities filled with X-ray emitting plasma. Now imagine countless such regions in the universe's first galaxies, their collective glow stretching across billions of light years to reach us as a faint, diffuse hum. The challenge is distinguishing this fog from other CXB components, like trying to separate the buzz of a distant highway from the static on an old radio. The smoking gun, metallicity. Early galaxies had less heavy elements, meaning their supernova exploded differently, potentially producing more X-rays per stellar death. Simulations show these low metallicity explosions could have flooded intergalactic space with hot, X-ray bright debris, some of which might still linger today as a fossilized glow. Telescopes like JWST have spotted hints of this, ancient galaxies with extreme star formation rates, their light tinged by the telltale signatures of violent stellar lives. If even a fraction of their X-ray fog survived cosmic expansion, it could subtly tint the CXB's spectrum, yet skeptics counter that stellar X-rays fade fast. Unlike black holes, which emit steadily for eons, star-forming regions quiet down once their massive stars burn out, typically within tens of millions of years. For their glow to persist, the early universe would need near-constant starbursts across every galaxy, a scenario that clashes with some models of cosmic evolution. Then there's the missing hard X-ray problem. Star formation typically generates softer X-rays, while the CXB skews toward higher energies. Unless early supernova operated under unknown physics, they can't explain the full background. Intriguingly, a compromise might lie in ultra-luminous X-ray binary systems where a black hole or neutron star feasts on material from a massive companion. Starburst galaxies breed these objects in droves, and their combined output could bridge the energy gap. The James Webb Space Telescope's detection of surprisingly mature black holes in young galaxies adds fuel to this idea. Perhaps early star formation didn't just make X-rays directly, but also sowed the seeds for later binary systems to amplify the signal. The answer may require listening to the cosmos in multiple wavelengths. By cross-referencing X-ray maps with infrared surveys of dusty starburst galaxies, astronomers could trace how much high-energy fog persists from different cosmic epochs. Missions like XRISM, with its exquisite spectral resolution, might even spot the chemical fingerprints of ancient supernova debris in the CXB's finest structures. What makes this mystery so compelling is its duality. It's not just about light, but about time. The X-ray fog could be a palimpsest of the universe's most formative eras, written in the death throes of its earliest stars. Whether it still whispers in the background or faded long ago, the search forces us to confront a deeper truth. The cosmos remembers its violent youth, and sometimes that memory lingers in the faintest glow. Not all X-rays are created equal. Some arrive with the subtlety of a whisper rather than a scream, carrying just enough energy to hint at their origins without giving away the full story. This is the enigma of the soft X-ray excess, a puzzling surplus of low-energy photons in the cosmic X-ray background that defies straightforward explanation. While most of the CXB's glow comes from high-energy processes like black holes and neutron stars, this softer component lingers like a half-overheard conversation, its source debated among astronomers for decades. Is it the faint breath of our own galaxy, or echoes of cataclysms that shaped our cosmic neighborhood long ago? One leading theory points close to home, specifically to vast clouds of warm gas drifting through the Milky Way. Imagine our galaxy wrapped in a delicate shroud of ionized plasma, heated to temperatures of around 1 million degrees. This gas, stirred by stellar winds and supernova shocks, could emit soft X-rays as its atoms collide and recombine. Observations from missions like ROSAT and XMM Newton seem to support this, showing the soft excess is stronger along sight lines through our galaxy's disk where such gas is densest. If true, it would mean part of the CXB isn't cosmic at all but a local veil, like mist on a window obscuring the view beyond. Yet skeptics highlight inconsistencies. Some patches of the soft excess appear too uniform to stem from the Milky Way's clumpy gas, and its intensity doesn't always correlate with known galactic structures. This has led to a provocative alternative. The soft X-rays might come from local bubble, a cavern of hot, thin gas surrounding our solar system, carved out by ancient supernova. Picture a series of stellar explosions millions of years ago, their shockwaves pushing gas outward to form a cavity roughly 300 light-years across. The lingering heat from those events could still be radiating soft X-rays, imprinting a local signature on the broader CXB. Supporting this, maps of the excess often align with the bubble's boundaries, as if tracing the walls of a cosmic furnace cooled to a faint glow. The debate takes a sharper turn when considering distant galaxies. If the soft excess were purely local, we'd expect it to vanish when looking far beyond the Milky Way. But some studies claim a residual signal persists, hinting at a truly cosmological component. Could there be overlapping contributions? Warm gas in galaxy clusters, for instance, might emit soft X-rays as it swirls in the gravitational pull of dark matter. Or perhaps the cumulative glow of countless stellar coronae, the superheated outer atmospheres of stars, adds up across the universe, a background hum of mundane but ubiquitous sources. The answer matters more than it seems. If the soft excess is galactic, it's a footnote, a correction to subtract from the CXB to reveal its true extragalactic heart. But if it's cosmic, it could signal unseen structures like the faintly glowing filaments of the warm, hot intergalactic medium. Future telescopes with sharper spectral resolution, like Athena, may settle the argument by isolating specific emission lines tied to local gas or distant plasma. Until then, the soft excess remains a tantalizing borderland between the near and far, a reminder that even the quietest light can hold the loudest secrets. At the farthest edge of cosmic X-ray background research lies a radical idea that hidden within its faint glow might be the fingerprints of quantum gravity itself. This isn't just about black holes or dark matter. It's about probing the fabric of reality on scales so small they defy imagination. If space-time isn't smooth, as Einstein theorized, but instead pixelated, a seething foam of quantum fluctuations, then ultra-high energy X-rays traversing the cosmos could carry subtle scars from their journey. These distortions, if they exist, would be vanishingly faint, like trying to spot ripples from a single raindrop in an ocean. Yet some theorists argue the CXB could be the perfect backdrop to hunt for them. Think of space as a vast, ultra-fine mesh. As X-rays travel billions of years, their interactions with this quantum texture might slightly shift their energies or arrival times. Certain wavelengths could scatter more than others, leaving a statistical anomaly in the CXB's spectrum, a barely detectable bump or dip at specific energies. The challenge, teasing this signal from the noise of ordinary astrophysics. It's like listening for a single out-of-tune violin in an orchestra playing at the edge of the universe. Current telescopes lack the precision to isolate such effects, but next-generation instruments like the proposed X-ray surveyor or Japan's X-RISM could get close, analyzing photons with unprecedented spectral resolution. The stakes couldn't be higher. Most quantum gravity models, from loop quantum gravity to string theory, predict some form of spacetime granularity, but at scales a billion times smaller than we can probe experimentally. If the CXB's photons bear marks of this granularity, it would be the first empirical hint of physics beyond Einstein's relativity, bridging the chasm between quantum mechanics and gravity. Some researchers are already scouring archival data for anomalies, focusing on the highest energy X-rays where quantum effects should be most pronounced. A few tantalizing outliers have emerged, tiny spectral deviations with no obvious astrophysical explanation, though skeptics caution they're likely instrumental artifacts or statistical flukes. What makes this search so electrifying is its sheer audacity. Even if the evidence remains inconclusive, the attempt forces us to confront fundamental questions. Is spacetime truly continuous, or does it have a resolution limit? Do photons interact with this hidden structure or glide effortlessly over it? The CXB, often seen as a relic of cosmic violence, might also be the universe's most delicate seismograph, recording tremors in the fabric of reality itself. Until we know for sure, this fringe idea stands as a reminder. Sometimes the boldest answers hide in the quietest whispers of light. What if the cosmic X-ray background isn't just a puzzle, but a flaw in the fabric of reality itself? That's the audacious claim of the simulation artifact hypothesis, a fringe but fascinating idea that dares to ask, could the CXB's unsolved anomalies be glitches in a programmed universe? While most scientists dismiss this as speculative fiction, the mere act of wrestling with it forces us to confront how thoroughly we've tested the laws governing our reality. Picture a video game where distant textures load imperfectly, creating faint visual artifacts at the horizon. Now scale that up to the cosmos. Proponents of the simulation argument suggest that advanced civilizations, perhaps our future descendants, might create hyper-realistic simulations of their ancestors' universe. In such a construct, the CXB could represent a computational shortcut, a way to approximate the background radiation of countless galaxies without rendering each one individually. The slight inconsistencies we detect, like the unexplained spectral bumps or odd anisotropies, might then be errors in the code, places where the simulation's algorithms falter under the weight of cosmic complexity. Of course, this sounds like science fiction, and to most physicists it is, but the hypothesis earns its sliver of credibility by making testable predictions. If the universe is simulated, its underlying code might impose subtle limits on how information is processed. Some researchers have proposed scanning the CXB for signs of quantization, tiny, discrete steps in energy levels that would betray a pixelated universe. Others hunt for unnatural correlations in X-ray data, patterns too perfect to arise from random astrophysical processes. So far, no such smoking guns have emerged. The CXB's fluctuations align beautifully with quantum mechanics and general relativity, leaving no obvious room for a programmer's fingerprints. Yet the simulation framework still serves a purpose. It's a stress test for our scientific assumptions. By imagining a universe where the CXB's quirks are intentional or accidental design choices, researchers are forced to clarify what natural really means. Take the hard X-ray excess, for example. In a simulated cosmos, it might reflect a rounding error in how high-energy processes are calculated. In ours, it points to undiscovered physics like sterile neutrinos or dark matter decay. Both explanations are speculative, but only one invites us to expand our understanding of particle theory rather than metaphysics. Critics rightfully argue that invoking simulation is a dead end. It explains everything and nothing simultaneously. But as a thought experiment, it sharpens our tools. The next time an X-ray telescope detects an anomaly, scientists won't just ask, what astrophysical process caused this? They'll also ponder, could this inconsistency reveal deeper laws? That dual perspective is the hypothesis's real gift, a reminder that even our strangest ideas can refine how rigorously we interrogate the cosmos. The simulation artifact hypothesis may never graduate from speculation to science, yet its boldness underscores a profound truth: the CXB isn't just light to be measured, but a mystery to be stretched. Whether the universe is code or pure physics, the act of questioning its rules is how we push knowledge forward. And sometimes the wildest roads lead to the most rigorous answers. We stand on the brink of a revolution in how we see the high-energy universe, a seismic shift powered by telescopes so advanced they'll peer into the cosmic X-ray background with unprecedented clarity. Leading this charge is Athena, the European Space Agency's flagship X-ray observatory set to launch in the 2030s. With a mirror 20 times more sensitive than Chandra's and a field of view wide enough to capture entire galaxy clusters in a single glance, Athena won't just observe the CXB, it'll dissect it. One of its primary targets, resolving the faintest X-ray sources that currently blur into the background's haze. Imagine zooming in on a pointillist painting until each dot becomes distinct. That's the leap Athena promises, potentially unmasking millions of hidden black holes, neutron stars, and other exotic objects that have eluded current instruments. Then there's LINX, a visionary concept designed to push resolution to its limits. While Athena excels at wide-field surveys, LINX would act like a cosmic microscope, imaging X-rays with razor sharpness. Its proposed high-definition X-ray imager could spot details as fine as the event horizon of a supermassive black hole in a distant galaxy, or pinpoint the faint X-ray glow from filaments of the cosmic web. These aren't incremental upgrades, they're quantum leaps. For context, LINX's spectral resolution might even detect the velocity of gas flowing through the warm-hot intergalactic medium, letting us track how matter circulates between galaxies like blood through veins. But the real game-changer lies in synergy. These telescopes won't work in isolation. Combined with gravitational wave detectors like LISA and optical behemoths like the Vera Rubin Observatory, they'll create a multi-messenger portrait of the cosmos. Picture this: LISA senses ripples from colliding black holes, while Athena simultaneously catches their X-ray afterglow, and Rubin maps the surrounding stellar carnage in visible light. Such coordinated campaigns could finally crack long-standing mysteries like whether primordial black holes contribute to the CXB, or if dark matter decay leaves subtle X-ray signatures. The hunt for dark matter takes center stage in these missions. Athena's X-ray integral field unit will scan galaxy clusters for anomalous emission lines at specific energies, potential fingerprints of sterile neutrinos decaying into photons. LINX, with its ultra-sensitive spectrometers, could trace the distribution of hot gas around dwarf galaxies. testing whether dark matter's gravity molds these faint systems differently than standard models predict. Some theorists even speculate these telescopes might spot dark galaxies, invisible structures revealed only by their X-ray halos, like finding silhouettes against a foggy sky. Beyond hardware, new analysis techniques will transform raw data into discovery. Machine learning algorithms trained on millions of simulated X-ray sources will sift through observations to flag anomalies human eyes might miss. Time-domain astronomy, tracking how the CXB fluctuates over years, could reveal transient events like tidal disruptions or neutron star mergers that currently slip through the cracks. And all-sky surveys, like those planned with ESA's new Athena satellite, will map the X-ray universe with such precision that even the faintest whispers from the cosmic web become audible. What makes this era so exhilarating isn't just the technology, it's the potential for surprise. Every time humanity has built a better window into the cosmos, we've found phenomena that defy expectation. Athena and Lynx might confirm our theories about the CXB's origins, or they might unveil entirely new classes of objects, forces, or even dimensions. The only certainty, the universe has kept its most profound secrets written in X-rays for billions of years. Soon, we'll finally be fluent enough to read them. From the eerie uniformity of the cosmic X-ray background to the missing baryon problem, from primordial black holes to quantum spacetime foam, we've journeyed through 25 of the universe's most perplexing enigmas, all hidden within a faint, all-pervasive glow. This isn't just a story about X-rays, it's a tapestry woven from the deepest threads of cosmology, astrophysics, and particle physics. Each mystery peels back another layer of reality, revealing how much we still don't know about the cosmos and how much more breathtaking the answers could be. Take the unresolved hard X-ray excess, for example. It could point to sterile neutrinos, dark matter decay, or even entirely new states of matter. Then there's the missing baryons, half the universe's ordinary matter seemingly vanished without a trace, possibly hiding in the warm, hot intergalactic medium's invisible tendrils. And who could forget the obscured AGN black holes so shrouded in dust they've evaded detection, quietly shaping galaxies while we strain to glimpse their muffled light. These aren't isolated puzzles, they're interconnected clues in a grand cosmic detective story. What makes the CXB so extraordinary is its universality. Unlike a single bizarre quasar or an unusual supernova, this background radiation is everywhere, a constant hum that every telescope hears. Solving its riddles wouldn't just fill gaps in our knowledge, it would force us to rewrite textbooks. Imagine confirming that primordial black holes exist or that dark matter decays into X-rays. Either discovery would send shockwaves through physics, bridging quantum mechanics and gravity, or revealing the true nature of the universe's hidden mass. But the real magic lies in the hunt itself. Every time we've built a better telescope, from Uhuru to Chandra to the upcoming Athena, we've peeled back another veil, only to find new questions waiting. The CXB is a reminder that the universe is far stranger, far richer than we've dared to dream. And the next breakthrough might not come from a massive observatory, but from a clever reanalysis of old data, or a grad student spotting an anomaly everyone else overlooked. So stay curious. The cosmos doesn't give up its secrets easily, but that's what makes the pursuit so thrilling. Whether you're an amateur astronomer peering through a backyard telescope or a physicist crunching equations at 3 in the morning, remember, you're part of this grand exploration. The cosmic X-ray background isn't just light, it's an invitation, a challenge flung across the void, asking us to look deeper, think braver, and keep unraveling the universe's greatest mysteries one photon at